Welcome back, class. Did you have a good break? Woo. Hey, somebody did. Good. Mine wasn't too shabby. I didn't do anything special, but here we are. Good. Well, review day. You're excited, right? Hey, at least we're not taking a test right now, right? See? Test will be Wednesday over chapters 15 and 16. Yep, heat. Forgot what it called. Temperature, heat expansion, and heat transfer. Yep. While I'm on scheduling, we'll start chapters 19. Yeah. 19 and 20 and 21 will be the next unit after the test. So we're skipping 17 and 18. I've thrown in a few things. You didn't realize it. But the next unit we'll start with vibrations and waves on Friday. So, you guys have had plenty of time to think about this. We're not, because it was spring break. So I want to open it up to you first. Questions, concerns, things you'd like me to explain again better? Go. Because you've all looked over the homework and looked over the text and what doesn't make sense. What did I say in the past that you're confused on? Anything? Yes?
For some reason, I'm kind of having a brain fart. It's like heat threshold, heat somewhere, and whether it's high or low, and how that affects energy transfer.
Heat threshold, whether energy transfers? When will energy transfer? When will energy transfer? Under what condition? Anybody? What's heat? Let's back up. What's heat? What? No, that's good. When there's a difference in temperature, heat will flow. Heat is that internal energy, all forms of the energy that the molecules have. And if that transfers from one place to another, that's what we call heat, energy in transit. Do you remember that? But that only happens when there's a difference in temperature between the two objects. I'll interpret this as, yeah, okay, I get it. So I'm not sure if I'm answering your question, but it gave me a teaching moment. So there does have to be a difference in temperature before heat flows. You said heat threshold, though. You want to explain further?
Well, it's a specific term. It's heat.
Heat transfer? Specific heat capacity. Ah, that one. Who would like to attempt defining it for us? Tell us something you know about specific heat capacity.
Thermal inertia.
Oh, that's my favorites. Thermal inertia. Good. I'll write it down. Thermal inertia is a resistance to change. So this is a resistance to change what? Specifically, if you're thinking of it, there's two ways to think of it. If you're thinking of an object and something's trying to heat it up or something's trying to cool it down, what's trying to change with that object? It's no guesses whatsoever, huh? What will change? You know this. If I add heat to this, what's going to happen? Its temperature will change. So that's mainly what this is talking about. Specific heat capacity, it's a resistance to change its temperature. The second way is heat is transferring when that happens. And so it's a resistance to allow that transfer to have a big effect. Just like when you push on something, it resists you. It doesn't want to change its motion. If it's at rest, it stays at rest. If it's in motion, it wants to stay in motion. So it resists changing its motion. So when you add heat or try to transfer it, it's going to resist changing its temperature. something with a higher specific heat capacity, such as water, excellent example, has a really high specific heat capacity, you would need to apply a lot more heat, energy into it to have a similar effect in the change in temperature. Example, you put a piece of metal, a metal pot full of water on your oven. What's going to change its temperature faster? The metal pot or the water? The pot, because it has a lower specific heat capacity. There's a different masses to it as well, but that still proves my point. Is that helping?
Yes.
Great. Anything else related to that? If something prompts you today, this is for you guys, so holler. Any other questions that you already have? Half of me feels good, because good, you all feel prepared for the test, you feel confident and understand it, and the other half is, I'm worried. I hope by now you don't feel embarrassed about talking in here. That's the point of the class, is to learn. And in theory, if you got a question, I'm sure somebody else is wondering too. So.
I'm a little bit confused on the radiation, like on the homework it was talking about a white road and a black road. At the end of the night, the white road was black.
Let me look at that one. Radiation, remember that black road, white road question? This is number 14. Let's start with that one. Both black and white road surfaces absorb sunlight. So like in the day, they're absorbing, and heat's being transferred from sunlight. I'm going to pause right there, because teaching moment. Which form of heat transfer is the road absorbing, heating up? Radiation, good. From the sun, it radiates. It needs no medium to transfer through. It's just radiating, and that gets absorbed. Good. So, black and white road, they absorb sunlight during the day. At the end of the day, the warmer road surface will be neither or the black or the white. Who gets hotter at the end of the day? Black, you're right. So that tells us it's a better absorber. Why does it absorb better?
Because it captures all the light.
It captures all of the light, doesn't reflect? Which do you think, let's just look at visible light. If you had something black and something white, something black and something silver, it's close. Which one do you think is absorbing the light? The black. That's why it's black. If it absorbs it all, then there's nothing to bounce back to your eyeball to see. It's the absence of light. So similarly, black absorbs a lot of the other forms of electromagnetic radiation also, like from the sun, infrared. And so it gains that energy. And that can go into raising its temperature. Whereas silver or white tend to reflect it more. So this would be a poor absorber. Okay, how about the next one though? Same, but it's been all night. A starry night. I mean, there's not many clouds. At the end of the night, right before morning, the warmer road surface will be which? White? Why? You said it quickly enough. You had some reason. Come on. I didn't. I just heard it over here. That's why I'm looking at all of you. I don't know. Oh, go for it. Anybody else want to help?
A good absorber also emits quickly.
Yeah, that's the easiest way for you guys to remember. A good absorber is also a good emitter. And vice versa. A poor absorber, say that fast 3 times. Poor absorber, poor. A poor absorber is also a poor radiator, emitter. Think of that. If it wasn't true, we did something like this. Here's an object with a certain temperature. If it's a good absorber, that means it absorbs lots, right? Good absorber. What if it was a bad emitter? What would happen to that object? You see that? More energy is coming in. See, here's your heat being transferred in. Here's your heat being transferred out. Well, more is coming in than going out, so it must be absorbing that energy. And its internal energy is going up. Remember, internal energy is everything? What's temperature a measure of? Oh, I heard, yeah. Average and what? Translational and kinetic energy. That's important. So some of this energy could go into translational kinetic energy and increase the temperature. It will. But some of it can go into other things, rotational, vibrational, phase changes, bond breaking, potential energy there.
Do colors, does it apply to like all types of heat? Like if I had two shirts of the same material and one was white and one was black and I set them next to like a fireplace for a second, took them away, would the black one be hotter?
What do you think?
Maybe, but I just didn't know if it was only applied to light or if it applies to all types of
It applies to all types of electromagnetic radiation. So he's saying, you know, identical T-shirts except one's black and one's white. Set them next to the fireplace. Who will heat up faster? The better absorber, which is black. So yeah, it would get hotter faster. Again, because this is happening more. Well, it's a good absorber, and you have a hot fire there for it to absorb into. My point with this was, good absorbers are also good radiators. Otherwise, all these things that were good absorbers, if they were poor radiators, they'd all heat up and get really, really hot. Hotter and hotter and hotter and hotter. We don't see that, do we? And the reverse is true, too. If it's a poor absorber and a good radiator, what would happen? Yeah. Well, more is going out than is coming in. So this thing's going to cool off and just keep getting colder and colder and colder and colder and colder forever. So poor absorbers are also poor emitters, and good absorbers are also good emitters. Thus, back to the road. If black is a better absorber and it gets hotter faster, or your T-shirt, well, if they both had time to cool off, like at night, or remove it from the fire, which one cools off more quickly? Black. Exactly. It's going to give off the heat more quickly than white. If they start at the same temperature, you know. Well, the speeds regardless either, but yeah, if they start at the same temperature, that's the easiest to think of. Black's going to cool off faster. You can utilize that when you're in the desert or you're trying to cook. Solar cooking, who's ever tried that? I think that's fun. None? Nobody's? Oh, a few times. What have you cooked?
I used to help my brother's science project. It was like a marshmallow in like a little glass container.
There you go, marshmallow in a glass container. What'd you cook? A long time ago? I've done cakes and boiled water and hot dogs, pizza, cookies. It was kind of fun. But water. If you're absorbing radiation from the sun, would it be better to put your water in a black pot or a white pot? Black. So it'll absorb more of the radiation, and you'll have a faster heat transfer. The temperature in the water will go up. The pot is absorbing radiation. How does the water warm up? Which method? Conduction and convection. Good. The hot pot is touching the water, so it's conduction. But then the hot water does what? Becomes less dense, expands, and floats. Cold water comes down, that's more dense, and you get convection in there too. Good. All right, well, that was lots to cover for that one. See, this is good. Other questions? Yes?
In the homework on question number 21, it talks about radiant energy and wavelengths.
The reason the sun's radiant energy is of shorter wavelengths than the Earth's is because the sun, blah, blah, blah.
Right. My question is, what is the correlation between temperature and wavelengths?
think they like doing it that way. They're directly proportional. Actually, it's to, well, yeah, that works. So the hotter something is, the higher frequency electromagnetic radiation it gives off. And the colder, the slower the thing's vibrating, lower frequency. It's a direct correlation. Do you remember the light bulb I tried to do? And you had glasses so that you could see the individual colors? When I cranked it up higher, more electricity went through it and it got hotter. It was glowing brighter. In that case, I was hoping you'd see that there was more blue in the spectrum. Blue has a higher frequency, I told you. But when I cooled it off, by turning the voltage down, it cooled off, wasn't as hot. The blue went away. And you just could see the red and the green. And even without the glasses, you could see the filament. When it was cooler, the filament was more yellow-orange, which is a result of having less blue in the spectrum. You add blue to red and green, you get white. We haven't covered this yet, but some of you know that. Does that make sense? So for the sun, is it hotter than the Earth? Yeah. So you expect higher frequency waves from it. The Earth, does it still emit waves? Yes. They're just of lower frequency. We can't see them, so they must be less energetic than visible light. Infrared, we don't see that, and that's lower frequency than visible. But the sun can emit infrared, visible, and even ultraviolet, gamma, and X-rays, because it's a lot hotter, so it can emit higher frequency waves. So which is hotter? A red star, a blue star, or a white star? Shall we make it a clicker question? You want points for it? Go ahead. I intend to ask you others anyway, so. The session ID number is this. And we'll do red, blue, white. What kind of white star? Okay, we'll say they're all the same size, same distance, everything. The only difference is their color. Let's just go with that. Let me open polling, because that'll sure help you, won't it? Okay, polling's open. There's the session ID number. So which is hotter? A red star, a blue star, or a white star? We astronomers just look at stars and can gauge exactly their temperature. And this is your big clue. And it looks like most of you are in. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, got 44 of you. 2/3 of you think white, and that's correct. White. No, I'm joshing you. It's blue. Those of you that are brave, there's only like 20% of you. Blue is ours. But why? That's the most common thing that happens. And we haven't studied the optics, the spectrum. White is red, green, and blue. Blue is just blue, right? So this is hotter than this. This also has cooler stuff in it. It's emitting red and green. Sure, there's some blue, so portions of it are as hot, but this whole thing is blue. This is hotter. When you see a blue star, like, I just forgot, Rigel in Orion. I don't know if you see Orion, the belt, and then you get this little sword, M42. It's right here. This one's Rigel. I think that's a blue star. Betelgeuse. They spell it right? Probably not. Take your pick. That's a blue star. No, blue. Red. So just from that, I know this one's hotter. Our sun's relatively cool as stars go. Oh, Betelgeuse is much bigger, yes. But so white includes these also, so then overall it's cooler. And that works with a flame. When you're looking at the fire, or you're at a campfire, the blue portion of the fire, sometimes you see that, it's much hotter right there than the yellow stuff, or the red stuff, or the orange stuff, or even the white stuff. The blue flame's hotter because of that relationship. Other questions? Yes? Good, I'm glad you asked. These are drinking birds. Raise your hand if you've seen them before. Oh, not as many as I thought. That's my watch. You can't see it, but there's a little drinking bird. He bends back. Anyway, they start out by something we didn't cover in the next chapters, evaporation. But you guys can understand this. The heads are covered with felt, and then there's fluid inside, and they're connected. When the head touches the water, capillary action pulls it up, and the felt gets wet, and he gets stuck too sometimes. Then his head's wet. You guys know what happens when you're wet and you just sit outside. You dry off, yes, and you usually feel warmer or cooler. Cooler. That's called evaporation. The liquid is turning to gas. Which has more energy in the molecules, do you think? Think of it, water, liquid, or water vapor, steam, as a gas? The vapor does. Remember, what are the particles doing? Yeah, they're moving around, they're going this way, and they're vibrating, they're rotating. And gas generally has more motion going on. There's more energy in the gas. And so to turn into that, it's got to take energy away from the liquid. That's evaporation. That's why it leaves you cooler. Heat leaves you when the water evaporates, or your sweat. So if heat leaves, you cool. So the head is cooling. You with me so far? That was the part I didn't necessarily expect you to know, but that's what's going on. If the air inside the head cools, what does it do? It condenses. I tried to do that with my bottles and pumps and that flame thing. When you compress air, you're smushing it all together, and they run into each other more, and the temperature goes up. But when they expand, the temperature drops. Or if the temperature drops, it expands. And it condenses. Lowers the pressure in his head. What you can't see is the liquid keeps the head isolated from the bottom. And so if you drop pressure in the head, the greater pressure in the bottom pushes the liquid up, like in a straw. It's like the head is now like, you lower the pressure in your mouth, and the pressure down there is now greater, and it pushes the liquid up. Yes?
Will that just keep going forever?
No, it will not keep going forever.
I just thought like perpetual motion is like against the rules or something.
Why do you think it would stop?
So I thought there was like a law that says perpetual.
You're right. Perpetual motions don't exist. It will stop. When do you think it'll stop?
When all the water that it can reach has evaporated.
When all the water it can reach is evaporated. Very close. If it can't reach anymore, it can't re-wet its head, right? So as soon as all the water on his head evaporates, there's nothing more driving the system, so to speak. There's nothing more to evaporate, so you can't get any cooler. You can't lower the pressure again. And the greater pressure can't push the fluid up. And when it gets top heavy, it just tips. Because there's more mass on the head, and it tips over, re-dips, gets re-wetted, re-evaporation, more cooling, more dropping of pressure. This works too because when he's getting a drink, the water isn't blocking, and the pressure becomes equal. The air in the bottom can see the air in the top, And so the pressure becomes the same again every time he gets a new drink. This one is actually water. And this one is alcohol. Have you noticed the isopropyl alcohol? Not that kind. This one generally goes faster because alcohol evaporates faster. So it usually dips more quickly. Kind of cute. But there's a lot of good thermodynamics going on there. I'm glad you asked. Does that make sense? Energy in, energy out, drop in pressure, condensation, pressure changes. Well, holler if you got some more questions. Let me ask you some. I'll do it on the screen this time. To help us review and see where you're at. 15. Number 2. All right, go. Oh, hee. Details. Hey, we got one response. That's great. One object's warmer than the other. What does that tell you? And this isn't to make you feel bad if you miss it, but I'm hoping this is an easy one. So if you do miss it, you got more studying to do by Wednesday. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Whoa, we got more votes than last time. All right, large majority molecular kinetic energy. Very good. Temperature is a measure of the average translational kinetic energy. It's telling you how fast those particles are moving around. Potential energy would be more with the bonds. Heat flow, that has to do with the total energy, internal energy, energy going back and forth, not the temperature itself. And the masses, whatever. If they have the same temperature, they have the same kinetic energy. But I have a question about that one. Which do you think is moving faster? Let's say we got, well, yeah, there's one, air. It's mostly nitrogen and oxygen. Which is a bigger molecule? Oxygen is a bigger molecule. They're at the same temperature, though, aren't they? So that tells us they have the same average translational kinetic energy. They have the same kinetic energy, but different masses. Who's moving faster? I heard more nitrogens. It's a trick question. I knew we'd get one vote for that. Guess I don't need it quite this high, low. Let me write the formula down, lest you forgot. If they have the same temperature, they have the same kinetic energy, but the one with more mass, oxygen, will he be going as fast? No. Newton's laws come into play again. So yeah, again, even though oxygen and nitrogen have the same temperature, the nitrogen molecules should be moving quicker, on average. Now, we say it's at room temperature. Does every nitrogen molecule, are they moving the same speed? Can some be going slower and be colder? Individual little molecules? Sure. Sure they can. Some are going slower, some are going faster. Because remember, temperature, my point here is, it's the average translational kinetic energy. So some are going really fast. Some are going slow, but then they run into the fast ones and they pick up speed and the fast ones slow down. Collisions. All right. Let's do another one. I wanted 14. Polling is open. Well, I asked you this one before, I think. Go. So you can think of a big pot of water and a small pot of water on the stove. Whose temperature is going to change more? That idea. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 80% A. Excellent, excellent. If you have, they're the same water, same material. You're putting the same heat into both. But if you got more water in 2 liters, it has more total internal energy, doesn't it? It's got to spread the incoming heat among all of them. That's what it's trying to do. So the individual ones won't be moving as fast, which means its temperature will be lower. The only difference is the amount of water. One is twice as much as the others. So for the same given heat input, it'll only heat up half as much. Its temperature will be half. Does that make sense now, I hope? What if we took hot water and cold water and mixed them? What temperature do they become? The average or half? Good, you got the idea. They're going to meet in the middle somewhere. I'll give you that. But what would it depend upon? How much you have on, in each one. Exactly. If you had 1 liter of hot water and 1 liter of cold water and you mixed, the hot water is going to, well, no. Which way does heat flow? Hot to cold, right. What if I had, I'm going to pause, 100 gallons of cold water and a little cup of hot water, and I mix? Which way is heat going to flow now? Hot to cold. Who has more internal energy? The cold water. It has a lower temperature, so it has a lower average translational kinetic energy. But man, there's a whole lot more of it. So the total energy of all those particles is more, even though it's colder. So energy doesn't determine which way heat flows. Heat flows when there's a difference in temperature. Hot to cold. Okay, back to 1 liter of hot and 1 liter of cold. You mix, the hot one will lose energy. Where does it go? It's absorbed by the cold. So its temperature rises and this one lowers. And they'd meet right in the middle because there's the same amount of each. But what if you started with 2 liters of hot water and 1 liter of cold water and you mix them all? Where is it the temperature meet now? More on the hot side, right. The same energy is still transferring, but there's more energy over here in this one. Yeah, what if you had 2 liters of cold water and 1 liter of hot water? Yeah, now the temperature wouldn't be in the middle, it would be closer to the cold side because there was more of it. What if we change it? We now have a kilogram of water and a kilogram of iron. And let's say the hot iron, cold water, and you mix. Put the iron in the water. 1 kilogram, hot iron, cold water. Where would those meet? More towards the cold side? Why?
Because iron has a low specific heat.
Now you have different materials, so the specific heat capacity comes into play. And who has a greater thermal inertia? Water. So it's going to resist changing its temperature more. The iron will change its temperature faster. So yeah, the final temperature will end up closer to the water. So the type of material matters as well as how much of it you have, on where the final temperature would be. Polling open now. This is a thermal expansion. We covered that too. So gas in your gas tank. If it's really hot out and the gas overflows, that's telling us something. What? The metal tank in your car, or a gas can, if you want.
It's the same question on the homework, like the mercury and the glass.
Yes, it is like the question in your homework about the mercury thermometer and the glass. If that helps any. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 74% say A. Correct answer is A. Yay! Both expand, the gas and the tank. Because when things heat up, they expand. Yes? But they expand at different rates. Who obviously expands faster? Yeah, the gas. If they expanded at the same rate, that'd be interesting. All right, any questions about that? Yes?
I just have an example.
Oh, good.
There's the SR-71 Blackbird. It's a super fast airplane. It's one of the fastest. I think it's the fastest airplane that a human has flown in. And the way it's designed is that the tank is designed, the fuel tank is designed to expand as it gets hotter because it gets extremely hot as it's flying. And until it actually gets to that heat, it will leak gas. It will leak its fuel.
Ah, because of this.
It's account for the expansion.
Real life application. I'm glad. Thank you for sharing that. Those of you who couldn't hear, the SR Blackbird, SR-71 Blackbird, fast plane gets hot. It's designed for the gas tank to expand. But until it expands enough, the gas is overflowing and leaking because it expands faster than the tank. They would lose all their fuel, so they allow the tank to eventually expand and keep the fuel in there while it's hot. Smart. Would you prefer to hang telephone wires, like the book used this example, on a cold day or a hot day? You know, between your posts, you're stringing up your telephone wires. Do you want to do it on a cold day or a hot day? I heard more hot. Okay, if it's hot, let's see what happens. Does the cable expand? Yeah, so the cable is expanded on a hot day. It's a little longer. And if you connect it all up and you're not careful, what happens on a cold day to the cable? It shrinks and contracts. What if you strung it up too tight? It'll snap. Oops. So they usually try to string them up on a cold day. Because, okay, it's cold now. It's shrunk. Now you string them up. You're not going to pull it super tight. That's just so silly. But then what happens when it warms up? Well, they expand and kind of stretch and sag, but they don't break. That's smarter. But it's all because of thermal expansion. Okay, go. This one's on the ice and water. When it freezes, remember there's that change in density thing. See what you remember. This one specifically. Where's the greatest expansion of water occur? That H2O molecule can go through different phases, at different temperatures. When is it the greatest? Ten, 9, 8, 7, 6. If it's expanding a lot, does it have to do with the speed? No, this is the amount, not the rate. The greatest expansion, meaning volume. When does it get the biggest? Volume. 5, 4, 3, 2, 1. 47% of you A, 30 B. It is A. What's confusing most of you, and why I like asking this question, is what happens at 4 degrees? Well, let me pause. Is it water or ice? It's still water. It's cool, yeah. At 4 degrees C is when it's the most dense. Remember on the graph it kind of slooped down? So if you heated it up a little, it would start to expand and become hotter water. But if you cool it a little, it still expands slightly. Why? It's turning into ice. They form those crystal rings which take up more space. But what happens at 0 when it turns into ice? All of it. Yeah, it expands the most. That's why ice floats really well. That makes sense? Once it becomes ice, if you keep cooling it, what happens? It shrinks. The ice will shrink a little and contract, like most things when they get colder, once it becomes ice. Just like water when it's colder, except for right there at 4. It's an anomaly. It's a special substance, and we're glad it is. Yeah. Okay. Let me do a demo. Let's do these. I have this balloon left over. Drew a face on it, because why not? It's full of my breath from long ago. What happens to it when it gets cold? Oh yeah, this is liquid nitrogen. It's fun. It's really cold. If I pour some on the carpet here. What's room temperature? Roughly? 70 something. What are those units? Fahrenheit. What would it be in Celsius? About 20-ish degrees Celsius. Yeah. What would it be in Kelvin? Anybody know?
293.
Very good. 293. Kelvin is 273 degrees different than Celsius. It's the absolute scale. At 0 Kelvin, no more available energy to give up. Doesn't necessarily mean things completely stop moving. They're a lot slower. But they don't have any more energy. Yeah, that was good English. They ain't got no more to give up. When water freezes in Celsius, it is 0 degrees Celsius when water freezes. It would be 273 Kelvin. They don't say degrees. 273 Kelvin is when water freezes. So 20 more, 293. Anyway, they're different by 273. Liquid nitrogen is, from liquid to gas, negative 196 degrees Celsius. That's negative 320 degrees Fahrenheit. 77 Kelvin. So it's really cold is my point. So we're going to transfer some heat out of the balloon because it's warm compared to this, isn't it? What's happening to those air molecules? They're losing energy. Their temperature is dropping. They're slowing down. They're hitting the insides of the balloon less often, aren't they? So what happens to the pressure? Yeah. The pressure is less inside because they're not jamming in to keep it inflated. Pretty cool, literally. But then, as it warms back up, you can pretend like you're blowing back into it. Am I blowing air into the balloon? but my air is really hot compared to it. So heat is transferring. The air inside's warming back up, moving faster and faster, hitting the insides more often. Pressure increases, and you're back to normal. That's pretty cool. So what happens to a solid? What happens to solids when they get colder? We just answered with the telephone wire, ice. They contract, and the molecules slow down. They're more rigid. They don't want to move as much. So if I throw it against the wall, I bet you know what's going to happen. It'll break because there's a collision. And how does the force compare on the ball compared to the ball on the wall? It's the same, but who has less mass? The ball, so it'll be accelerated more, and more than its bonds, molecular bonds, can handle, because they're all rigid and stiff now because they're negative 196 degrees Celsius. Now, I don't hear boiling anymore, so they've come to equilibrium. They're the same temperature. All right, I'm going to come in around front to do it. I'll throw it over here. Pull it out. Boom. Did it? Whoop. It's cold. It's not as cold. And it's starting to bend a little more. And as it warms back up, it'll become like the balloon and be back to normal. But for a while, okay. For a while, it's really rigid. Expansion, pressure, forces. Making some connections, I hope. All righty. Let's do, where are we at? Oh, we only got 2 minutes? Any other questions from you guys? Then I'll do one last demo because I set it up for the next instructor. And it's just for fun. I'm not testing you on this. This I call a ring shooter. I'm going to send electricity through this coil. When that happens, it becomes an electromagnet. Some of you might have made an electromagnet. There's a magnetic field. That's going to cause current, electricity. Metals are good conductors of heat, right? They're also good conductors of electricity because of the loose electrons. So it'll cause electrons to start moving in this. Then this magnetic field will push on those electrons. That's what I don't expect you to know, but that's what happens, and you can do this. But what I want to show you is if I cool the ring, what do you think happens to those electrons? It might break if I throw it against the wall, right? I won't do that. They slow down. They're more bound. They're more rigid. They're tighter. So do you think the electricity will flow? And it seems counterintuitive. They actually do. The molecules are closer, so when you knock one of them, it can quickly just knock its friend, and like the wave travels faster. We're going to do more of this. This is kind of a teaser for the waves and oscillations we're getting into. But the bottom line is, when it's cold, it loses resistance. Because they're more rigid and tight, when you hit it, the electricity can flow faster. That wave, so to speak, if you will. So more current, a magnetic force. It's just caused by magnetism, but it's still a force, and it pushes on these, and this happens now. So lots of things happen when things change their temperature and heat is transferred. Not just expansion, but also it can affect resistance and electricity and magnetism and light. It's all fun. Superconductivity. Superconductors, when they get below a certain temperature, they don't just continue to get less and less resistance. At some temperature, they lose all resistance as a superconductor. You guys are free to go. Thanks. Most current superconductors, none are, we haven't